In the last video, we saw the density operator rho for pure state, that is, a quantum system whose state psi is known exactly, for which the density operator rho can be written as the outer product of psi. Now, if we don't have the 100% knowledge of state psi, then it is known as a mixed state, and with the help of a simple criteria, we can determine whether a state is pure or mixed. If trace of rho square is equal to 1, then the state psi is pure, and if the trace of rho square is lesser than 1, then psi is a mixed state. Now moving further with the concept of density operator, let's take a composite system A and B described by the joint density operator rho AB. Now we know that trace of the composite system A and B would be equal to trace of A into trace of B. On the same note, we can define the partial trace. Suppose for A, partial trace of A into the composite system A1 A2 tensor product B1 B2 would be equal to trace of A1 A2 into B1 B2, where this trace has the usual operation. Similarly, the partial trace of system B would be equal to trace of B composite system A1 tensor product B1 B2 equal to A1 A2 into trace of B1 B2, where A1 A2 and B1 B2 are the vectors in the state space of A and B. Now let's define the reduced density operator. The reduced density operator for a composite system AB is a mathematical object that describes the state of the subsystem of the larger system. It's a way to trace out the degrees of freedom of the other subsystem, leaving only the relevant information about the subsystem of interest. Given a composite system AB with a joint density operator rho AB, the reduced density operator for a subsystem A is obtained by taking the partial trace over the other subsystem B from the joint composite system. To understand it better, suppose a quantum system is in the product state rho AB equal to rho tensor product sigma, where rho is the density operator of system A and sigma is the density operator of system B. Then the reduced density operator rho A would be equal to partial trace of B into rho AB, which would be equal to partial trace of B rho AB is rho tensor product sigma. Now partial trace of B would be tracing out the subsystem B given by sigma, which would be equal to rho into trace of B, and this trace will be equal to 1 since trace is for diagonal element. Therefore trace of the element of sigma I outer product sigma I can be written as sigma I, and this is equal to 1 from the orthonormal condition. Therefore this value would be equal to 1, which leaves rho A equal to sigma. Similarly, we can see that rho B equal to partial trace of A over the joint system rho AB, which would be equal to trace of A, and rho AB equal to rho tensor product sigma. Now partial trace of A would be tracing out the subsystem A, which is given by rho, which would be equal to trace of rho into sigma. Again this value would be equal to 1. So rho B will be equal to sigma. Now let's see an example to understand the reduced density operator with the help of a Bell state beta 0, which is equal to 0 0 plus 1 1 by root 2. So this has a density operator rho, which would be equal to outer product of beta 0, which would be equal to 0 0 plus 1 1 by root 2 into bra of 0 0 plus 1 1 by root 2, and multiplying it will get rho equal to 0 0 outer product plus 0 0 1 1 plus 1 1 0 0 plus 1 1 outer product 1 1 divided by. Now let's try to find out the reduced density operator of first qubit by tracing out the second qubit. So rho 1, which is the reduced density operator for the first qubit, will be equal to partial trace of second qubit over the joint state rho. So rho 1 would be equal to partial trace of second qubit of rho, which is given by this expression. Now we are taking the partial trace of the second qubit, which implies the first qubit will come out from here and we'll have the trace of the second qubit. Similarly, for this, the first qubit will come out and we'll have the trace of the second qubit. Again, for this state, the first qubit will come out and we'll trace the second qubit, and again doing it for the 1 1 case. doing the similar operation for these two states, we get, now we know trace of AB will be equal to inner product of BA. So writing it in inner product form, we'll have rho 1 equal to outer product of 0 into inner product of 0 plus outer product of 0 1 into inner product of 1 0 plus outer product of 1 0 into inner product of 0 1 plus outer product of 1 1 into inner product of 1 1 divided by 2. Now we know this inner product and this inner product will be 0, and this inner product would be 1. So rho 1 would be equal to outer product of 0 plus 1 divided by 2. And from the completeness condition, that is summation I ai would be equal to the identity operator, where ai are the orthonormal basis set. Similarly, our zeros and 1 are the computational basis set which satisfy the completeness condition. So rho 1 would be equal to I by 2. We can also realize this operation since we know 0 state is equal to 1 0 and 1 state is equal to 0 1. So outer product of 0 state would be equal to 1 0 into 1 0, which would be equal to 1 0 0 0, and outer product of one state would be equal to 0 1 into 0 1, which would be equal to 0 0 0 1, and adding those two will get the identity operator I. Hence our reduced density operator for the first qubit is I by 2 for the beta 0 Bell state. Now let's check whether this state is pure or mixed. Now we know trace of square of the density operator equal to 1 implies the state is pure state, and if trace of the square of the density operator is lesser than 1, then the state is mixed state. So using that info, we can find out whether this state is pure or mixed. So trace of rho 1 square would be equal to trace of I by 2 square, and we know trace of I by 2 is equal to 1. So trace of I by 2 square would be equal to 1 by 4 plus 1 by 4, which is equal to half. So this would be half, which is lesser than 1. That means this state is a mixed state. Now this is a remarkable result since the joint system of two qubits is a pure state, that is this state, since we know it exactly. However, the first qubit state rho 1 is a mixed state, that is we do not have maximal knowledge about. Isn't it strange that we have complete information about the joint state but the subsystem is less known to us? Well, that's quantum entanglement for you. So I hope you understood the concept of reduced density operator.